All right, so I want to go over a quick example of I would call it a fairly basic related rates problem. I think it's a concept that's confusing, and what CPM does, I've noticed, is that they make the problems um, very difficult. And I think that it's important to just kind of do an easy one to see what's going on before we start getting into the difficult related rates problem. So a related rates problem happens when we have something that's changing and it's changing as a result of something else. Okay. Sounds kind of vague when I say it like that, but let's think of the example. Water leaking onto a floor forms a circular pool. The radius of the pool increases at a rate of 4 centimeters per minute. How fast is the area of the pool increasing when the radius is 5 centimeters? Okay, so a lot of stuff is given to us. The information that we need is how fast is the rate of the area pool increasing at a particular point in time. Okay, so I would recommend trying to solve this on your own. Maybe pause me for a second to try to solve it if you have time, but I'm just going to go ahead and solve it. When we have a related rates problem, we usually need to connect it to some other. Usually it's a geometric formula that we know. In this case, it's the area of a circle. The area of a circle is area is equal to pi r squared. One way to think of this would be area as a function of t is equal to pi r, which is self as a function of t squared. And I'm going to work on the one on the left, but the one on the right gives you a good way to think of it. So when I'm solving it, I'm going to take the derivative with respect to t, and I get dA dt is equal to 2 pi r dr dt. Okay? And then I can plug in the things that I know for it. Okay, so the radius of the pool increases as a rate of 4 centimeters per minute. That means that dr dt is equal to 4. It means that r is equal to 5. How fast is the area of the pool changing? It means what are we looking for? dA dt. And so if I plug those numbers in, I'm going to get dA dt is equal to 2 pi times 4 times 5, which is 40 pi. And the unit is important on related rates problem. It's how fast is the area of the pool increasing. So area is measured in this case in centimeters, and area is centimeters squared per minute. There's your answer. And it won't always be this straightforward. We could do another example where the variable that you're looking for isn't automatically isolated on the left-hand side after you take the derivative. In fact, let's do that. Again, you can pause it and do number 2 if you want. Oil is spilling from a ruptured tanker. Oil spilling from a ruptured tanker spreads in a circle on the surface of the ocean. The area of the spill increases at a rate of 9 pi meters squared per minute. How fast is the radius of the spill increasing when the radius is 10 meters? Okay, so let's think of what do we have here? We have another area of a circle question. I'm going to take, actually, maybe it'll be helpful to list the knowns that we have here. So the oil spill increases at a rate of 9 pi meters squared per minute. What you may think to yourself, what is that? Well, that's dA dt. So dA dt is equal to 9 pi meters squared per minute. When the radius is 10, and then you might want to say to yourself, what are we looking for here? How fast is the radius? We're looking for dr dt. So it's going to work pretty similarly to the last one where I'm taking the derivative of the whole thing with respect to t, and I'm going to get a prime is equal to 2 pi r prime. And I'm just showing you that either of these forms of notation is fine, dA dt or a prime. And then I'm just going to plug in 909 pi is equal to 2 pi times 10 times r prime. And r prime would equal 9/20. And what would the unit be? Well, this is how fast the radius is changing. And the radius is increasing not in meters squared per minute, but meters per minute. So hopefully that gives you a decent idea of how you look at a related rates problem. These are all problems that are going to be applied to things that are physically happening. So keep in mind what these symbols mean. dA dt is the rate of change of area with respect to t. dr dt is the rate of change of radius with respect to t. In both of our examples that we did, something was leaking, which meant both dA dt and dr dt were increasing. But a lot of times dA dt or dr dt, a lot of times things will be decreasing. And sometimes you'll have relationships where necessarily one thing decreases with reference to the other. Like a lot of times you'll have pictures of triangles where maybe it's a ladder and one thing is the ladder is sliding. So this thing is increasing or decreasing. The height is decreasing, the length is increasing. So keep in mind that that's what those things represent. And in your head, you should be cataloging whether those things are positive or negative when you go through a related rates problem, in my opinion.